In this lecture, we will discuss the method of computing Galois groups using reduction mod P. We begin with the following theorem, which is given in our basic settings. So we have: let R be an integrally closed domain and F be the field of fractions of R, and E be Galois extension of F, and finally S be the ring of elements in E integral over R. And finally, let P be a prime ideal in R. Then there exist finitely many prime ideals of S lying over P, and these are permuted transitively by the Galois group G of the field extension E over F. The key point of this theorem is that the action of the Galois group on the set of prime ideals lying over P is transitive. For the proof of this theorem, we need the following lemma. Let Q1 through Qn be prime ideals in S, and let A be an ideal in S such that A sits inside of the union of these ideals Qj's. Then for some J, A belongs to one of these primes ideals Qj. We may assume that A sits inside the union of Qj's, but is not covered by the union of any proper subset of the set of ideals Qj's. Then we may choose for each I an element AI in A which belongs to Qi but does not belong to any Qj with J different from I. What we are trying to prove is that the number of the ideals in this minimal cover is equal to 1. And let us assume, by contradiction, that n is greater than 1. Then let us form for each I elements Bi that are products over J different from I of Aj. This construction will only fail when n is equal to 1, because in this case the product is empty. What we have is that Bi belongs to Qj for all j different from I, and bi does not belong to ideal qi since qi is prime. Here each factor does not belong to qi, and then because the ideal qi is prime, the product also does not belong to qi. Now consider element b, which is the sum I goes from 1 to n of bi's. This element belongs to ideal A because each element bi belongs to ideal A. Well, since all factors ai's are in A. And then, since we have that ideal A is covered by the union of qj's, then there exists k such that element b belongs to qk. But we also have that for all I different from k, bi belongs to qk. And since the whole sum belongs to qk, so we conclude that bk belongs to ideal qk. But this is a contradiction, because by our construction, each element bi was not in the ideal qi. The source of this contradiction was our assumption that n is greater than 1, hence n is equal to 1, and our ideal A belongs to a single prime ideal qj. Now let us use this lemma to prove our theorem about transitive action of the Galois group on the set of prime ideals. We know that the Galois group acts on the ring S and it fixes elements of the ring R. This implies that the Galois group will act on the set of prime ideals in S that lie over a fixed prime ideal P in the ring R. Let's give the proof of the theorem. We know that the Galois group acts on the ring S and it fixes elements of the ring R. This implies that the Galois group will act on the set of prime ideals in S that lie over a fixed ideal P in the ring R. Let Q1 be a prime ideal in S lying over a prime ideal P in the ring R, and let Q1 through Qn be the orbit of Q1 under the action of the Galois group G. Let Q star be another prime ideal in S lying over P. We need to prove that Q star belongs to this orbit. Fix some element S in the ideal Q star and consider the product over sigma in G, sigma of S. What can we say about this element? So here each factor belongs to the ring S because S is G invariant. Moreover, this product belongs to Q star since one of the factors is S, which is element of Q star. Also, we can say that this product belongs to F since it is, by construction, G invariant. And the set of all G invariant elements in E is the fixed field F. But then we conclude that this product belongs to R, since R is the intersection of F with S. This holds because R is integrally closed. And every element of F which is integral over R belongs to R. But then this tells us that it also belongs to ideal P, which is the intersection of Q star with R. So this is because Q star lies over ideal P. And then this tells us that it also belongs to Q1, because P sits inside Q1. Now we recall that Q1 is a prime ideal. And if the product belongs to Q1, then one of the factors belongs to Q1. So this tells us that there exists sigma in G such that sigma of S belongs to Q1, which tells us that S belongs to sigma inverse of Q1, and thus S belongs to one of the ideals in the orbit of Q1. Since S was an arbitrary element of Q star, we conclude that Q star is covered by the union over I goes from 1 to n of Qi's. And then by lemma, there exists a J such that Q star sits inside one of the ideals Qj. But these two ideals have as intersection with R the same ideal P. And we proved in this setting that we must have equality of these two ideals. So Q star is equal to Qj, and we proved that this arbitrary prime ideal Q star, which lies over prime ideal P, must belong to the orbit of Q1. Hence, the action of the Galois group on the set of prime ideals that lie over P is transitive. With our next theorem, we want to understand better the structure of the ring S as an R module. This theorem will also help us with computations of S in specific examples. Theorem. Again, so we assume that we are in our basic setting, like on this diagram, and assume that R is integrally closed. Then S is contained in a finitely generated R module, and if R is Noetherian, this will of course mean then S is a finitely generated R module. From the proof of this theorem, we will also see how to look for generators of S as an R module. Let us give a proof of this theorem. By primitive element theorem, we can write E as F extended with alpha, where alpha is an element of E. And we know that E is a fraction field of S. Moreover, we know that there exists R in R, which is non-zero, such that R alpha belongs to S. And here we can replace alpha with R alpha as a generator of this field extension. So without loss of generality, we're going to assume that alpha is an element of S. Let f be the minimal polynomial of alpha over the field f, and suppose n is the degree of this polynomial f. So then, if we take the set 1 alpha, alpha squared, up to alpha to the n minus 1, so this will be a basis of E as a vector space over F. Instead, we let M to be an R module generated by the same set 1 alpha, alpha squared, up to alpha to the n minus 1. Since alpha and all of its powers are in S, so we see that M sits inside S. We would like to understand how far S could be from M. Our claim is that S sits inside 1 over D times M, where D is the discriminant of the polynomial f, which is determined by the generator alpha. So D is the product over I less than j of alpha I minus alpha j squared, where alpha i's are the roots of polynomial f. So here the claim is that S sits between M and 1 over D times M. Our extension E is Galois, so in particular E is normal over F. This means that an irreducible polynomial which has a root in the field E factors as a product of linear factors. So f of x can be written as the product over I goes from 1 to n, x minus alpha I. And the Galois group acts transitively on the set of roots, alpha I. And by our assumption, one of the roots is an S, and G leaves S invariant. So from here we conclude that for all I, alpha I is an S. Consider an arbitrary element S in the ring S. We want to show that S belongs to 1 over D times module M. Now we know that E is f of alpha, and alpha is an element of degree n. So this means that S can be written as a n minus 1 alpha to the n minus 1 plus a1 alpha plus a0, where ai's are elements of f. Now let us denote this expression as g of alpha, and let us set sj to be g of alpha j. So alpha j's form an orbit under the action of the Galois group. So this means that there exists sigma in G, such that alpha j is sigma of alpha. But then, since the coefficients of the polynomial G are in F, so this tells us that sigma of S is equal to G of alpha j. So this is Sj. And because S is invariant under the action of G, so we conclude that all Sj's are elements of the ring S. Now we want to do linear algebra and treat AI's as indeterminates. then we have that the column vector S1 through Sn is equal to some matrix A times the column vector A0, A1 up to An minus 1. Now, what is the matrix A from this system of equations? So the matrix A will have entries that are AJ's raised to the power I. So here J goes from 1 to n, and I goes from 0 to n minus 1. And we see that this is a Vandermonde matrix. And the determinant of this matrix is the square root of the discriminant. So it's the product over I less than j of alpha I minus alpha j. Since every alpha I is in S, we see that the determinant of A is in S, but the square of the determinant, which is the discriminant of the polynomial f, is also G-invariant. And for this reason, it's not only in S, but it's in the intersection of S with f, which is equal to R because R is integrally closed. Consider the formal adjoint matrix for matrix A. So that is the matrix that is made up of cofactors. So let B be the adjoint of A transpose. Then from linear algebra, we know that B times A is equal to determinant of A times the identity matrix. Consider now the following product. Let's take determinant of A times B times the column vector S1 through Sn. This equals to determinant of A times B times A times the column vector A0 up to An minus 1. And because B times A is a multiple of the identity matrix, what we get is that this is equal to discriminant times the column vector A0 up to An minus 1. But everything in the left-hand side is in S. So this tells us that for all I, AI belongs to 1 over D times S. And since element S is a linear combination of powers of alpha with coefficients AI's, so from here we get that little s belongs to 1 over D times the R module M. And since element S was arbitrary, this tells us that as an R module, S is a submodule in 1 over D times M. By construction, the module 1 over D times M is finally generated. Its generators are powers of alpha divided by D. And if R is Noetherian, then we know that any submodule in a finitely generated R module is itself finitely generated. And this completes the proof of the theorem. And now we have the following corollary. Let R be Z and F be Q. Then there exists a basis of E over Q, which consists of elements of S. So we have that Z is Noetherian, and by theorem S is a finitely generated Z module. Since we are in a field of characteristic 0, this Z module cannot possibly have torsion. So this means that S is actually a free Z module of a finite rank. This means that S is Z beta 1 plus Z beta k. And we know that elements of E can be written as fractions S over R, where S belongs to S and R belongs to Z, and of course R is non-zero. This tells us that the set beta 1 through beta k spans E over Q. And since we know that betas are linearly independent over Z, this also tells us that they are linearly independent over Q. Because if we have a linear dependency over Q, we can take least common multiple of all denominators, and multiplying the linear dependency by this integer, we can clear out all denominators and obtain a non-trivial linear combination of betas with integer coefficients, which is a contradiction. So the conclusion that the set of betas is a basis of E as a vector space over rationals. Now let's consider an example. Let's take E to be a Q with a joint square root of 5. And we would like to describe the ring S, which is elements integral over Z in the field E. Here, the generator of this field extension, root of 5, is integral over Z. Indeed, the minimal polynomial of square root of 5 is x squared minus 5, which is a monic polynomial with integer coefficients. And the module m in this case is z times 1 plus z times square root of 5. Since 1 and square root of 5 are integral, so this is a z submodule inside S. And from the proof of the previous theorem, we see that S is in between m and 1 over d times m, where d is the discriminant of the polynomial f. So let's compute d. So we have x squared minus 5 factors as x minus square root of 5 times x plus square root of 5. And d, which is the product over I less than j, alpha I minus alpha j squared. So in this case, so this will be square root of 5 minus negative square root of 5 all squared, and this is 2 square root of 5 squared, which is equal to 20. So this means that S will be between m and 1 over 20 times m. And if we carry out a more detailed analysis of S in this case, then one can show that S is a free Z module of rank 2 with generators 1 and the golden ratio, 1 plus square root of 5 over 2. Next, we are going to prove our main result about Galois groups and reduction mod P. Let us write down the statement of the reduction mod P theorem. Let f be a monic irreducible polynomial in Z of x. And let f bar is equal to f mod p. So the reduction of this polynomial mod p. So this will be a polynomial in Zp of x. And we factor f into irreducible factors in Zp of x. And we factor f bar. So f bar is f1 times f2 times fr. Assume that all irreducible factors are distinct and have degrees d1 up to dr. Then the Galois group G of this polynomial over Q, which is a subgroup in Sn, where n is the degree of f, contains a permutation which is a product of independent cycles of lengths d1, d2, dr. This theorem allows us to extract information about the Galois group in characteristic 0 by looking at the reduction of the polynomial mod p. Let's give a proof of this theorem. Let E be the splitting field of this polynomial over Q. And let M be the degree of E over Q, which is also the order of the Galois group G. Let S be the ring of elements in E that are integral over Z. So from our previous corollary, as a Z module, S is a free Z module of a rank M, where M is the dimension of E over Q. This tells us that the quotient of S by PS is Zp to the power M, and so the size of this quotient is P to the power M. Let P1 through Pt be prime ideals in S lying over the ideal generated by P in Z. The ideal generated by P in Z is maximal. This implies that the ideals PI's upstairs are also maximal in S. Indeed, we proved earlier that if Pi sits inside some ideal A and Pi intersected with Z is equal to A intersected with Z, then this implies that Pi is equal to A. Consider a homomorphism Psi from S to S quotient by P1 plus S quotient by P2 plus S quotient by Pt. Let's compute the kernel of this homomorphism. Well, obviously, the kernel of Psi is the intersection I goes from 1 to t of Pi's. Let us call this ideal D. Then we can factor this homomorphism through the quotient ring S quotient by D. So let us call this Psi bar. So then we will have that Psi bar is injective. Since prime P belongs to each ideal Pi, it follows that D contains the principal ideal generated by element P in S. So Ps is in D. And thus we have a surjective map from S quotient by Ps to S quotient by D. And from here it follows that the size of S quotient by D is less or equal to P to the power M, which is the size of S quotient by Ps. We claim that the map Psi bar is also surjective, which means that S quotient by D is actually isomorphic to S quotient by P1 plus S quotient by Pt. This is a version of Chinese remainder theorem. Let us fix one of the indices I. We recall that we cannot have Pj being nested inside Pi, because we cannot have nested prime ideals lying over the same prime ideal in Z. This means that there exists Bj in Pj, which is not in Pi. And then we form Ci, which is the product over j different from I of Bj. Then we see that Ci belongs to Pj for all j different from I, and Ci does not belong to Pi because the ideal Pi is a prime ideal. So if none of the factors is in Pi, then the product is not in Pi either. Then if we look at Psi at Ci, then we see that this projects to 0 in each component S quotient by Pj, where j is different from I, and projects to non-zero in S quotient by Pi. But the ideal Pi is maximal. So this tells us that the quotient S by Pi is a field. This implies that if we have a non-zero projection to S quotient by Pi, then any element of this quotient may be obtained as an image under Psi. So we conclude that S quotient by Pi belongs to the image of Psi. And since this can be done for any I, so this tells us that the map Psi bar, which has the same image as Psi, is surjective. And we have an isomorphism of S quotient by D to this direct sum of these fields. We also know that the Galois group acts transitively on the set of prime ideals P1 through Pt. So this tells us that all fields S quotient by Pi are isomorphic. And let us denote this isomorphism class as K. Again, because we have a surjective map from S quotient by Ps to S quotient by Pi, so this tells us that K is a finite field. And obviously it will have characteristic P. So this tells us that the size of the field K is P to the power little k for some K. We saw from this decomposition that S quotient by D is isomorphic to K to the power T. And then by counting, since we know that the size of S by D is less or equal to P to the power M, so this tells us that M is greater or equal to KT. Let alpha 1 through alpha n be the roots of our polynomial f. So this means that f of x is the product I goes from 1 to n, x minus alpha I. Since this polynomial is monic, so we conclude that for all I, alpha I belongs to S. And let alpha 1 bar through alpha n bar be images of alphas in the quotient S quotient by P1. Then we have that the reduced polynomial f bar of x factors as the product I goes from 1 to n, x minus alpha I bar over this finite field S quotient by P1. We compare this factorization with the factorization over ZP. So we have F1 times F2 times FR. We know that the roots of each irreducible polynomial over ZP are distinct. So of each Fi are distinct. Irreducible polynomials over a finite field cannot have a multiple root. And by assumption of our theorem, Fi was different from Fj for I different from j. By comparing these factorizations, we see that some of the alpha I bars are the roots of polynomials Fj's. And then we see that alpha I bar is different from alpha j bar for I different from j. Let H be the stabilizer of P1 in G. These are all elements of G that do not move P1. Since H of P1 is P1, so this tells us that H acts on S quotient by P1. And so we have a homomorphism from H to the Galois group of this finite field. From the orbit stabilizer formula, we see that the order of H times the length of the orbit, which is T, is equal to the order of the group, which is M. From here, we conclude that the order of the stabilizer H is equal to M divided by T, and from our inequality, this is greater or equal to K. Let us look at this homomorphism. Any element of the Galois group is determined by what it does to alpha i's. So every non-identical element of H will induce a non-trivial permutation of alpha i's. But when H acts on S quotient by P1, it permutes alpha I bars in exactly the same way as it permutes alpha i's. And since all alpha bars are distinct, this means that any non-trivial permutation of alpha will induce a non-trivial permutation of alpha bars. And so this homomorphism is injective. So we get an injective map from H to the Galois group of K over ZP. But our field K has p to the power little k elements. And we know that the Galois group of such a field is isomorphic to the cyclic group ZK generated by the Frobenius automorphism. But we saw that the order of the subgroup H was greater or equal to k. And here we have injective map into ZK. So this tells us that this map has to be surjective, and H has to be isomorphic to a cyclic group ZK. Let tau be the generator of H that gets sent to the Frobenius automorphism of K. We pointed out that tau acts as a permutation of alpha 1 through alpha n in the same way as the Frobenius acts on the roots alpha 1 bar through alpha n bar in K. Now let us look at the factorization. F bar is the product of F1 times F2 times Fr. Roots of each Fi generate a finite subfield in K. And this tells us that the Frobenius of K will act transitively on the set of roots of each Fi. And this tells us that as a permutation of alpha 1 through alpha n, tau is a product of disjoint cycles of lengths d1 through dr, where dj's are degrees of polynomials fj's. And this completes the proof of the theorem. Let's make the following remark. So when we factor f bar into irreducible factors, we have a requirement that fi is different from fj when I is different from j. How strong is this restriction? It turns out that there are only finitely many primes for a given polynomial f for which this requirement fails. Indeed, if fi is equal to fj, then their roots are the same. And this tells us that sum of the alpha k bars will be equal to alpha s bars, with k different from s. And then, if we consider the discriminant, which is the product over I less than j of alpha I minus alpha j squared, then this will be equal to 0 mod p. So we see that this requirement fails only for prime divisors of the discriminant d of the polynomial f of x. Next, let us consider an example on application of this theorem. Example: compute the Galois group of the following polynomial over Q. So f of x is x to the power 4 plus 10x cubed plus 5x plus 15. So first we know that by Eisenstein with p equals 5, we conclude that f of x is irreducible. Let us look at reductions of f mod other primes. So if we do reduction mod 2, then we get f bar of x is x to the power 4 plus, so this will become 0, so we get x plus 1. And we can see that this is irreducible in z2 of x, because reducible polynomials of degree 4 in z2 of x either have roots, and this polynomial does not vanish not at 0, not at 1, or another possible reducible polynomial in z2 of x of degree 4 is x squared plus x plus 1 squared, which is x to the power 4 plus x squared plus 1. And this polynomial is not this one. So this means that this is irreducible, and the conclusion is that the Galois group of f contains a cycle of length 4. Now let us reduce this polynomial, mod 3. Then here f bar of x is x to the power 4. So here this will become x cubed plus 2x, and the constant term becomes 0. So this factors as x times x cubed plus x squared plus 2. And this polynomial has no roots in Z3. So the value at 0 is equal to 2, the value at 1 is equal to 1, and the value at minus 1 is equal to 2. And because a cubic polynomial that has no roots is irreducible, so this becomes a factorization into irreducible factors. And the conclusion is that the Galois group of this polynomial over Q has a cycle of length 3. And this Galois group is a subgroup inside S4, because our polynomial has 4 roots in the algebraic closure of Q. And we see that the order of G is divisible by 12, because this group has elements of order 3 and 4. So this tells us that the order of G is either 12 or 24. But A4 is the only subgroup of order 12 in S4. And A4 does not contain a 4 cycle, because 4 cycle is an odd permutation. And our conclusion that this Galois group is isomorphic to S4. Let us mention a result about permutation groups, which can come quite handy when we are trying to prove that a particular Galois group is isomorphic to the full group Sn. Proposition. Let G be a transitive subgroup in Sn which contains a transposition and a cycle of length n-1. Then G is equal to Sn. Let's give a proof. So without loss of generality, we can assume that G contains the following cycle of length n-1. 2, 3, 4, up to n. We can make this assumption just by relabeling the elements in the n-1 cycle. And also assume that this group contains some transposition AB. An important fact to remember about permutation groups is how conjugation works in Sn. So if we conjugate a cycle I1, I2, Ik with the permutation mu, then the result will be again a K cycle that permutes elements mu of I1, mu of I2, mu of Ik. Our group G is transitive. So this means that there exists a permutation mu in G such that mu of A is equal to 1. And then if we conjugate with this mu the transposition AB, the result will be some transposition 1C, and this will be in G. Let us denote this cycle of length n-1 as tau. Tau acts transitively on the set 2, 3, 4, n, and index C belongs to this set. Then this tells us that there exists K such that tau to the power K maps C into 2. And then if we conjugate with tau to the power K our transposition 1C, then the result will be that the transposition 1, 2 is also in the group G. If we multiply now 1, 2 with permutation 2, 3, n, then this product can be easily checked is equal to the n cycle. 1 goes to 2, 2 goes to 3, 3 goes to n, and n goes to 1. So let us call this n cycle eta. Then if we conjugate with eta the transposition 1, 2, then the result will be transposition 2, 3. If we conjugate 2, 3 with eta, we will get the transposition 3, 4, and so on. So what we see is that all adjacent transpositions are in G, but adjacent transpositions generate the whole symmetric group. So this tells us that G is equal to Sn. This result may come handy in conjunction with reduction mod P theorem when we need to prove that the Galois group is Sn. In conclusion, let us mention one important open problem in Galois theory. This is called inverse Galois problem. Let G be a finite group. Construct a Galois extension E of the field Q with Galois group of this extension being isomorphic to G. We know how to solve this problem for many families of finite groups. So, for example, we know how to do it for symmetric groups, for alternating groups. We know how to solve this for all solvable finite groups, and even for most sporadic finite simple groups, which are pretty exotic. However, it appears that we are not close to the final solution of this problem, and definitely new methods and insights are required in order to attack it in full generality.